In this video, we're going to extend our definitions of the trig functions to include not just trig functions of acute angles only, but trig functions of any given angles theta, maybe sketched in standard position. And so the way we're going to do this is actually, as a matter of fact, sketch a general angle over here. And I just want to kind of point something out here. What we're going to do is we're going to borrow from the fact that if we had, say, some angle in standard position, we'll call this angle theta. So in standard position, this means that it leaves from the positive x-axis. And maybe it terminates here in the first quadrant. We say we have some angle theta. The idea is if we were to have a point on the terminal side, and this is the key to the matter here. If we were to have some point on the terminal side, that would be a wonderful thing. And the reason why is because what we could always do is drop an altitude from this back to the x-axis, and what we've done is formed a right triangle. And the nice thing about having a point on the terminal side is if you knew this point xy on the terminal side, well then it would be fair to say that we would have to know that the height of this triangle would have to be the same as the y value of this point right here. So what we could say is the height of this triangle is y. The width or the base of this triangle here would have to be x units out. So we say the base is x, and then by definition what we're going to do is we're going to call the hypotenuse r. But what this allows us to do is redefine the trig ratios. We could even do this with, say, SOHCAHTOA here. But if we said, let's go find the sine of this angle, the sine, recall, so would be opposite over hypotenuse. In other words, what we would get here is essentially this. We would get the y value of this point over the length of the hypotenuse here. Okay, and that is exactly how you'll see me define it over here. We say the sine of an angle in standard position is always going to be equal to y over r, where y is the y value of this point on the terminal side, and r is the hypotenuse length. Okay, and if we wanted to find, say, the cosine of this angle, recall that the cosine of theta, it would be adjacent over hypotenuse, and in this case we get x over r. In other words, all we would need to know is the x value of this point. We could take that x value and divide by the length of the hypotenuse, and we would have the cosine value. So, over here in our definition, we say that the cosine of any angle drawn in standard position would be equal to x over r, where x is the x value of this point on the terminal side over the length of the hypotenuse. And then last but not least, we've done sine. Sine is y over r. Cosine is x over r. Let's define the tangent of an angle. The tangent theta of an angle would then be the opposite over adjacent. In other words, just take the y value of this point on the terminal side divided by the x value of the point on this terminal side. So what this essentially means is we could evaluate the 6 trig functions of any angle theta sketched in standard position so long as all we know is a point on the terminal side. So that's kind of a nice thing to have, okay, these definitions here. So using these 3 definitions, we say sine is y over r, cosine is x over r, and tangent is y over x. We could actually define the other 3 trig functions or their reciprocal functions just by flipping these original 3 over using the reciprocal identities, okay? So the benefit to using this definition is that not only does this work for acute angles theta, but let's say I were to rotate this over to here, some angle right here, we could say, all right, so there's my angle theta. And in this case, theta would be an obtuse angle so long as I had this point xy on the terminal side, xy. What we could say is then I can still drop an altitude and I can still form a right triangle. I know that the height of this triangle is y, that the width of this triangle is x, and that the hypotenuse is what we're going to be calling r. Okay, so we're going to be using this definition to find the 6 trig ratios of any function in standard position so long as you know a point on the terminal side. Before we do that, however, one thing I do want to do is this. I want to define how is it that if I knew a point on the terminal side, x and y, then we could go solve for r. And looking at this picture right here, of course we have a right triangle, so it is fair to say that this is always the case, that the x value squared plus the y value squared of this point, since they're the legs of this triangle, would be equal to the r value squared. And in a nutshell, what we want to say is this: if we're solving for r, then we say that the value of r is actually always equal to the square root of x squared plus y squared. Okay, so our new definition of the 6 trig functions of an angle theta in standard position is essentially this: so long as you know a point on the terminal side xy, we could say that the sine of the angle is the y value over the length of r, cosine is the x value over the length of r, and tangent is the y value over the x value, where r is always equal to the square root of x squared plus y squared, and r is never 0. And last but not least, we say r is always positive. Okay, that length from the origin out to the point xy will always be considered a positive length. Okay, so x may be negative and y may be negative, but there will never be an instance where r is negative. So one real quick note here before we use this definition that I want to make is this. We say since r is equal to the square root of x squared plus y squared, since it can't equal 0, it follows that the sine and cosine functions are defined for any real value of theta. That is something we already knew, that you can always find the sine or cosine of an angle. But basically what I'm saying is since r is non-zero, it'll never be 0, and the definition of sine and cosine are y over r and x over r respectively, will never divide by 0 in those instances. I did say this though. We say, however, if x equals 0, then say tangent and secant would be undefined. You could see this here. We say tangent would be over x, and we say secant is over x. So if x were 0, then we would say those would be undefined. And likewise, we could say that cotangent and cosecant, if you were to ever have a value of y that is 0, that is, you have an angle that possibly terminates right here. Maybe it starts on the positive x and it terminates over here at pi radians. We would say that this point on the terminal side, maybe it's like -1, 0. It has a 0 for a y value. So its cosecant and cotangent would be undefined since that y value would be 0. Okay, so what would this look like in practice? This is, as a matter of fact, a really easy thing to do. So I'm going to give you some wisdom here. Let's go ahead and take a look at it. It says let -3, 4 be some point on the terminal side of an angle theta. I want to go find the sine, cosine, and tangent of this angle. Okay, so rule number one is this: draw or sketch a picture. So sketch the angle theta. So I'm going to do that first of all. As a matter of fact, what we've been told is this, and if I had graph paper, it would look a little bit better, but we say -3, 4. So we go left 3, up 4, 1, 2, 3, 4. We know that this point is on the terminal side of our angle. So what I'm going to do is I'm actually going to sketch in the terminal side of our angle. We do have to sketch the angle itself. So we don't know what this angle is, but we're going to call it theta in general. And the last thing I want to do is I actually want to drop an altitude here. And so I'll switch colors just to kind of emphasize this here, but always drop an altitude and label the sides of this. So here's our right triangle. We know that the height is 4. We know this because that is the y value of this point. We say -3, 4. And we know that this right here, this bottom leg, I'm going to write a -3 on this. The only thing we don't know is r. So my next bit of wisdom is this. We're going to list and or find x, y, and r. If we're going to use these definitions of sine, cosine, and tangent and their reciprocals, then we need to know all 3 of these values here. So we were already told an x value and a y value. The only thing we don't know is the r value. That's okay. We'll go find them. So my suggestion is this. Let's go write x equals, y equals, and r equals. And I want to make this as standard as possible. So we say x. Well, we already know that the point on the terminal side is -3 for an x value, has a +4 for a y value. And as far as the r value goes, you might as well just get used to writing this here. We get -3 squared plus 4 squared. And so this gives us the square root of, sorry to go outside the box here, the square root of 9 plus 16, which is the square root of 25, which gives us plus or minus 5. Now, the thing to be clear on is this. We're going to stick with the positive. And the reason why is because if we talk about r is defined as being the distance from here to this point to the origin, from this point to the origin, okay? So essentially, r is always positive, and I'm going to write a 5 here. So now that we've sketched our picture, and we've listed x, y, and r, we could actually just go find the sine, cosine, and tangent of this angle here. So we say the sine of this angle, the cosine of this angle, and the tangent of this angle are defined thusly. We could say that the sine of this angle is the y value over the r value here. So we would say we get y, which is a +4, over 5, which is also positive. So we get a positive sine value. And basically the sine of this obtuse angle, for the first time we can do obtuse angles, is just 4/5, okay? Now how about the cosine? So the cosine, recall that cosine is the x value here over the r value, and in this case our x value happens to be negative, which is fine. A negative divided by a positive though, however, you'll see that our cosine value actually comes out to be negative. And then last but not least, we say tangent. What would the tangent of this angle be? By definition, the tangent of any angle theta in standard position is equal to the y value of this point on the terminal side divided by the x value of this point on the terminal side. In other words, 4, in this case 4 divided by a -3, and that's it. That's all she wrote. As a matter of fact, it's a really easy set of definitions to use to go find your trig functions. So again, let's try this one last time. We'll check out of this video here, but we say let's let the point 2, 3 or 2, -3 be a point on the terminal side of the angle theta. So the nice thing about this is we already have a point on the terminal side. We'll go right 2, 1, 2, and we'll go down 3, 1, 2, 3. And we say that we've been told that this point 2 comma negative 3 is on the terminal side of our angle. So we're going to go ahead and sketch this angle in. We say here is the angle. It's very important. If you don't draw that angle, then you've not really represented this. But we say, okay, so here's our angle. What I want to do is I want to drop an altitude and label the parts of this triangle. So the parts are these. We say the y value is negative 3, the x value is 2, and the one value we haven't found yet is r. So here's my picture. We've sketched the angle. What we want to do now is list x, y, and r. So we say x. Well, we know x is 2. We know that our y value is negative 3. And we also know that the r value would be equal to the square root of x squared plus y squared. So in this case, we're not going to get a beautiful number or a perfect square on the inside of this radicand, but we get 4 plus 9. So we get root 13, okay, and this is our r value. So now that we have x, we have y, and we have r, let's go ahead and piece together the sine of theta, the cosine of theta, and the tangent of theta. So here we go. We say sine. Sine would be this y value over the r value, which we know the r value is root 13. So we'd say we get a negative 3 over root 13. As a matter of fact, we should rewrite that as negative 3 root 13 over 13 when we rationalize it. So there's our sine value there, negative 3 root 13 over 13. Cosine. Now cosine by definition is our x value divided by our r value, or x on our triangle here divided by our r value. So in this case we get positive 2 over root 13, which when rationalized comes out to be 2 root 13 over 13. And then last but not least, we say our tangent value. I like the tangent value the best because it's a little bit easier to do most of the time. We say it's y over x. In this case, we get a y value of negative 3 and an x value of positive 2, so we get negative 3 halves. But that is how we use this definition of trig functions. So long as you know a point on the terminal side, you're in good shape. Cheers.